Yeah, start. Yes.
Okay. So listen, you ping Peter?
I have, yes.
Okay. So the idea today is to talk a bit about the VMs in general. We will be talking more about the Cairo-vm because it's the one that we made a prover for, but and the one we coded in Rust, not myself, not Diego, but the great team of the Cairo-vm. Well, Marian, we have Marian. And for those who don't know him, he worked both in the prover and in the Cairo-vm, maybe installed in Rust. I'm right? Yes. So if we have some time at the end of the talk, I will mention installing Rust, that because it's important to prove a blockchain, but we are some steps away from installing Rust. So the idea is to discuss mainly the VMs. Hopefully shed some light into all of this. So, just to recap some things we have been talking before, we have two ways of proving something in general. The more snark-based approach is using a specific circuits for each program that gets compiled. That's called an ASIC way, and the circuit is specific for that program. What we are going to try to do with stars is a bit different because we are going to leverage the fact that if you remember the transition constraints, they are kind of cyclic. You say the next step is going to follow these rules, the next step is going to follow this rule, the next step is going to follow these rules, and these rules are always the same. And so we are going to try to define a set of rules or constraints that are going to represent a VM. We could do this in using not a custom VM like Cairo. Maybe we can try to prove a common CPU architecture. Maybe we can prove RISC-V, and that's what the people at RISC-0 are doing. The idea of the Cairo-vm is to have a VM designed for this. So you will see that instead of working with binary arithmetic and integer arithmetic like usually computers do, the Cairo-vm is going to work with a finite field arithmetic. And so, since the finite field is native for the constraint system and the star, it's going to be a bit more efficient if everything is alright. So, I will start by showing a bit the process of proving a Cairo program. So we are going to start with the Cairo program that maybe you have seen. If not, I can show you the Cairo program. We should have many in our repo. For example, Fibonacci here, a Cairo program that looks something like this. That this is really readable by a human. It looks like Python. The new version it looks like Rust, but it is very easy to read. And what we are going to do is to call the compiler and get into the Cairo assembly. In this case, it's a special set of instructions that is designed for the Cairo-vm. This is the thing that the Cairo-vm really executes, not this code. Once the code gets compiled to the Cairo assembly, we are going to send it to the Cairo-vm. And the Cairo-vm is going to execute the code. The special thing about this VM is, leaving aside the special arithmetics and optimization for the finite fields, is that it's going to print the state of the VM at each step. So that is what we are going to prove. In particular, it's going to output two things. One thing is called in the documentation the trace, but it's not really going to be the trace that we are going to prove. So it's a bit confusing. So I'm not going to use that term anymore for this trace. We are going to call it the register state. The VM has three registers that gets updated, like a program counter, a frame pointer,
Allocation.
and the location pointer. So it has this pointer that gets updated with each step. And then we have the memory. The memory is just a big table with the memory, like a normal computer. And the prover is going to pick all of this, build like the real trace that is going to be proven. That is a bit different to this. We are going to take a look at it later. And then output the proof. So this is like the whole path of the program from the beginning to the end. If you use our Cairo program, you can just feed it the Cairo assembly or the Cairo program assisted by the main file. We call the Cairo-vm Rust internally, and then the prover, all in the same program. But if you use, for example, the stone prover or other proofs, sometimes you have to call the Cairo-vm outside and then feed the memory and the register state to the prover. Any questions? Okay, if there isn't any question, I will continue. So let's see how it's proven and take a look at the code. As I said, the core idea is not that complicated. We are going to have, we need to design a set of constraints that represent the Cairo-vm. This is done in a start with an error. So, because if you remember from the last classes, the last talks, the error is a representation of the constraints in start. So let's find the Cairo error in our repo. So this is the prover, the Cairo prover, this will be the definition of the error. Let me find the main constraints. As you can see, there are around 59 columns. And there are many constraints. So this is all things that we will see later. Oh, here we go. So what we have here is just this. We compute instruction constraints, some constraints related to the operand, some constraints related to the registry, to the output codes. If we take a look at this, it's just unpack the constraints and, well, this is it. You can find all the set of constraints that you need to prove the VM in the Cairo paper, which is really good. But here we have it all. Now, I told you before that we are not actually proving what the VM is outputting, but something a little bit different. What we are going to call the trace. So what's the difference between what we are proving and the thing that the Cairo-vm is outputting? The idea here, if you remember the stars, is that improving transitions, right? So we don't have a place where we can write the memory, for example. There is no table. There isn't any table with the memory. There is only the transition between each step and between all the execution of the Cairo-vm steps. So what we are going to do is to kind of augment the original trace. We call it augmenting, and I think we have here the code. Oh no, this is the documentation, and you can see it in the documentation too. So if we go to the landmark GitHub, you will see this. And yes, we are going to merge the state of the registers and the memory and start doing transitions that kind of have everything in the trace. It has not only how the steps have evolved, but which position of memory they use and which value they use. So let me find the documentation, should be here. Maybe this is better if you see it here. So this is a small diagram of the real trace. You can see that what we will have is the decoded instruction flags, some values that we need to prove, and all the memory addresses are here too, like each instruction, which memory address it uses and which value it uses. And you may ask, okay, but maybe I have this instruction and it doesn't use any memory access, or maybe not all of them, because it's working with immediate values that are encoded in the instruction. And in that case, well, the bad luck. You will still have to have all the columns and put something in there. What is going to happen is that the constraint that represents that instruction won't care about the memory values, but the trace will look the same. So, everything clear? Any question until now? We get the trace, the memory, and we are going to generate with it the real trace that we are going to prove.
Yes.
Yes. Carlos?
Mauro, is not there an intermediate step in StarNet that would be Sierra?
Yes, I did this where I show the Cairo program and it compiles to Cairo assembly. If this is Cairo 0, this is true. And if it is Cairo 1, it is true, but you have an intermediate step where the Cairo program compiles to Sierra and the Sierra compiles to the assembly.
Great.
Sierra is an intermediate language.
Mauro, the one thing you just show those X. Can you show again?
Yes.
Those are that's the state of the VM. Right?
Yes, that represents a step of the VM or a state of the VM at one point. Yes.
So what we need to prove is the sequence of states, basically.
That's right.
Okay,
that's
perfect.
Correct. So we are proving the sequence of states. That's totally right. Oh. And you will see some columns that are more auxiliary values, but more or less it's the same. And of course, you start seeing some things like, okay, I have a column for one flag, right? And that flag can be a 0 or a 1 because it's a flag. But the start trace has fields that can be a number from 0 to 2 to the 252 with this field. So you can say you are kind of wasting the full potential of the field because you are using zeros and 1 and you have a lot of numbers. Once again, well, bad luck. It's what you have to do. You will see this also in stars. Sometimes you will need to represent some binary arithmetic or some binary values, and you will be forced to do this. But at least we will get some optimizations with the memory values where we try to still work with fields even when we might try to simulate some binary arithmetic. But let's keep that for later. Okay, so this is the general approximation to proving a Cairo program. But then things are going to start get a little bit more complicated. So Diego explained before this term that was called RAP, or randomized R with preprocessing, if I remember correctly, which enables you to prove that something is a permutation that the column is a permutation of another column. That's what it does. And this is going to be key, a key element to prove the VM. So as I said before, we won't have a centralized place with the memory in the trace. Instead, we will see that each instruction is saying, okay, this instruction use this position of the memory, and in this position of the memory there was this value, right? So what happens if another instruction comes and says, I'm using this position of memory, and now there is another value? And we have to remember that in Cairo, the memory is read-only. Or if you are working in the VM, you say you are just writing one time. But for the purpose of the prover, it is something that is read-only, and its values can change. So if I have three instructions that are trying to use the same position of the memory, and they are saying to me that they have different values, that should fail. So that's what we call that the memory must be single value. Then we have another constraints about the memory. We should have it all here, I think, but it should be incremental. And I'm missing one, but we have this kind of constraints. And if we have to show, for example, that some part of the memory is incremental, or that it is single value and the values are not ordered, the constraint will be a really big mess, and it's going to have a really high degree. So the trick here is that we are going to order the memory by address, and that way the constraint to show to you that it is incremental, for example, is really easy, because you only have to check the previous value. So each previous value of addresses must be the same or one smaller. And the same will work for another thing that we call the range check. And if you have programming Cairo, you might know about the range check built-in, but that's not it. This is just the range check. Is an easy constraint that is used both by Cairo and Maidan. And I don't know if I reach 0. I'm sure that by those two. That what it's going to say is to establish a value between 0 and 2 to the 16. And it's going to be very, very useful, because some values like the offsets of the operands in the instruction has to be constrained by the range check. Okay, so going back, we have a permutation. Then we are going to use the wrap that you have already learned to prove that something is a permutation, and add some extra constraints. And if you go to the code, you will see exactly that. We have this constraint that checks that the memory is increasing, and it's doing something more. We have to refactor that. And it's just what I told you. No, nothing too mysterious. It uses the sorted values. So now things are starting to look more like they work. It's more similar to the real case, but we still have to add more things. So any question until now? Okay, then we can continue. Now, if I just do this, I'm proving that I have correctly executed a code in the virtual machine, and that's not very useful. If I have a transaction in the blockchain, or if I run a program, it's not the same if I did 2 + 2, or if I did a token transfer. I need to know exactly which program was executed by the virtual machine. And here's when things are going to get a little bit messier. What we are going to do is the following. We are going to add artificial accesses to the memory, like saying, okay, we are going to pretend that we have accessed some places in the memory, and in that place, in those places, we are going to have the instruction of the program. That's in the code is not so easy because you can just add an instruction and pretend that it accessed a position of the memory, because that probably won't be not be complying with the other constraints of the virtual machine. So we are going to have to do that in a smart way. The smart way here is, okay, we are not going to add any instructions, but what we are going to do is to add to the memory cells, to memory address and memory value of some column, pair of columns that is not constrained by any instruction, but is going to be part of only the memory constraints. So it's going to affect the wrap, it's going to affect all that is related to the memory, but nothing that is related to the instruction. In our current design, we have specific columns for that. We will see that Starware does things a little bit different, but the core idea is the same. Maybe I can show you the trace column, the execution trace. Hopefully it is here or in the error. So this fourth column that we have, or fifth column that we have, is just for that. But this is the order one, the sorted. We should have the non-sorted here. Okay, well, I'm not finding it right now, but one of these constraints should be affecting only when we generate the trace. Maybe we can look at it later, but we are going to start adding this memory, artificial memory access. Okay. So now I have added some artificial accesses to the memory to add the program. And that's still useless for the verifier, because it's okay, you add to me some more data that I can check, that you tell me that it's valid, and it is valid, it doesn't affect the program, you can add whatever you want, but the verifier still doesn't have any way to check which program was used. So what we are going to do is quite straightforward. If you remember the wrap, it was like a grand product of things that it should be zero in the case, in the normal case. I don't know if you remember the constraints, but we can go to the Cairo paper, and you will see them at the end. This should be chapter 9, permutations. So it's something like looks like this equality. And when we add the memory, the only thing what we are going to do is we are not going to add this artificial access to the memory to the initial values, only to the sorted ones. And that is going to mean that these products are not going to be the same, right? So, but that is going to be really useful for the verifier, because what the verifier is going to do is to say, okay, these values shouldn't be the same. I'm going to check this wrap, but I know which program should have been executed. And if I know which program has been executed, I know the extra values added to the sorted memory access, memory addresses and values. So it's going to kind of fix the equation, knowing the values of that comes from the program, and then by doing that, it can check that the that the program executed is the one it expects. And that's like the first version of doing it. So is it clear? At least a general idea. We can dig into the equations later. So that's the core of the basic prover for me. I don't know if you will add something more, Marian. Okay, that's more or less the core. Then some things will happen that maybe we want to pass the program to the next power of 2, because we want to do a Fourier transform, if you remember, as an optimization. And how do we pad these two traces? If I just add garbage to the end of the trace, the constraints won't work, and it's going to say this is garbage. I can't verify this. So what we will do to pad, and there are more reasons to pad sometimes the code. For example, well, let's start with this one. In this case, we need to kind of fill the program with more instructions or with more data, but we can't just place whatever we want. So the solution in the Cairo-vm is using something that is called proof mode. And you will see that when in any of the Cairo-vms that have been implemented, that they have something called proof mode, and the compiler has something called proof mode. And we can see the code of proof mode in Cairo-lang. And you will see that it is really an easy solution. I wanted to open the proof maybe with an underscore. I don't want, I'm searching for issues, right? No, I want to search for code, proof. I missed the repo, right, Marian? Okay. If not, I'm just going to spoil to you guys what does it do, but I thought it was in Cairo-lang.
It is, but it is a bit.
Okay. Well, if Marian now finds the code, I can show it to you, but what it's going to do is replace, kind of change a bit the code that we want to prove. So the main function of your program is not going to be the main function anymore. We are going to add one instruction at the beginning that calls the main function. And then it's going to return to one instruction, and the last instruction of your program is going to be an infinite loop, a sham relative to itself and to 0. So the purpose of this infinite loop, that is not going to be executed an infinite amount of times, of course, but we are going to start filling our program with calls to this loop until the program reaches like the amount of steps that we need, in this case for doing an optimized Fourier interpolation or operations in general. So with this proof mode, since you can always execute another step of an infinite loop, and it's going to be complying with the constraints, because an infinite loop can go on and forever, and it doesn't matter. We are going to pad the trace whenever we need it, we did. There might be another situation where we need to pad the trace. And some edge cases, I don't know. What happens if I have less steps than program instructions? So now our trace is going to be a little bit unbalanced, right? Because you're going to have more rows in the ones related to the memory, and less in the ones related to, like, more rows on the artificial accesses to the memory and less on the real steps of the VM. So when you have that kind of unbalanced trace, you will have to pad something and balance it again so proofs can work. Any questions? Yes.
What is it? More of a general question. What makes a CKVM a CKVM? Is it things like this? Like it's more friendly to make proofs out of the computation traces? Or is it like that, or is there something else?
No, for me, like if you want to say CKVM, as long as it generates a trace that can be proven or some elements that are kind of a trace that can be proven, it is a CKVM. Then you can do an optimized one for finite field arithmetics, or maybe use like V0, a VM that is executing RISC 5 or whatever, but as long as it outputs something that can be proven, we can say that this is a CKVM. At least for me, it's not like there is an organism that is going to tell you that's a CKVM or that's not a CKVM.
No, because now that you explain it, it's like it's really just a name. It's not like too complex to me. I mean, it's a CKVM. It's just something that you can make a proof out of it, right?
Yeah. For me, that's enough. Okay. Then you have sometimes CK EVMs that what they try to do is instead of using something like RISC 5 or a specific VM, they try to execute the EVM, the Ethereum VM, and generate a trace that can be proven. I think
yes.
Kakarot, Triton is a CK EVM. I think on Polygon. I'm not sure. I don't remember.
Yeah, basically it generates a trace and it has an architecture that is like that makes the math more simpler, or tries to make it as simple as possible. That's why, for example, Cairo has only 3 registers, and its memory is write only.
Read only.
Read only. Sorry.
Oh, my mic's off. my auto turn off his mic. That's right.
Mariano, you're still off.
We are all out.
There is no sound.
I stopped the mic because I went to get some water. And Marian kept talking in India.
Sorry, I was talking and I was muted. So, what makes the VMCK is like that. Just it generates a trace and it has an architecture that is like good for making a proof. That's basically it. Yes.
If we are talking about like CK rollup, what's the proof that we will post on the main chain or what?
Sorry, what happened with the CK rollup?
Yeah, when we are talking about CK rollup, what's the thing that we will post in the main chain?
Yes, we are going to usually post a proof of a specific program that represents like if you didn't have CK, what would you do in a L1 or in Ethereum? You kind of execute every transaction. You do it right, and it gets executed in many computers. The rollup is going to do the same. The only thing is at some point it's going to generate a trace for that execution, and it's going to get proven. It's going to say, okay, I have executed all these transactions, and the diff between the states is going to get published at the L1. Does it make sense? We are going to need some more tricks for that, but yes.
Okay. Yeah, it kind of does. It is like somehow like some miracle tree that I will post in the main chain to change the state, or there is something more or more complicated than that.
No, let's go there, but let's go in steps. So now we have some more problems because we are trying to prove something in the blockchain. So maybe we have this case where we have to run a lot of programs. I'm not. So yes, I have to run a lot of programs and make one proof for the L1. So let's see how do we run many programs. What we're going to do to run many programs is use something called, at least this is Starnet spec. I don't know all the other blockchains. We can use something called a bootloader. So the idea is that instead of proving a specific program, we will have a bootloader like the ones that we usually use in any computer. That what it's going to do is to load code from many programs or from many traces and prove them all together. And the verifier is going to check that the bootloader was executed, and for each program you will have published the hashes of the program, so people can know which program has been used. That's like an easy case. And if you want to prove the blockchain, I'm still sharing my screen, right? Yes. So you can use something called the Cairo-vm, for example. That's what the standard uses. This is not going to work. I never find it quickly. Cairo. Oh, that's great. So this is what is sent to the L1. This Cairo-vm is just that, is the whole operation of the blockchain and the state. It's not a market tree, it's a proof of all the executions that happen in the blockchain. When I mentioned standard in Rust is kind of like the thing that the blockchain is using when not proving, when it wants to go fast. But when proving, you have to use this OS. That answers the question?
Oh, yes. Thank you.
There are some small issues like with the memory, because now the program has the bootloader has to assign some spaces of the memory for each program, so it becomes a little bit more messier. When you have only one program, all the memory is for that program, and you're done with it. But leaving aside that it's a bit more complicated, is the idea. Okay.
Can you talk about like the prover size or the proof size and the proof times?
The proof size?
I heard there's like you need like gigabytes, like 500 gigabytes of memory to generate the proof and stuff. Is that true?
Gigabytes of memory for a proof? No, the proofs are small. They are in the order of at most kilobytes. Or we are talking about the memory usage of your computer. I'm not understanding.
Yeah, like to generate a proof, how much computational power do you need?
I don't know. I haven't tried to prove the Cairo-vm yet. Um, ish-
But maybe one of the ones we know.
For yes, a small proof it can be running in your computer. Um, um, yes, I don't want to say I don't have any numbers for the blockchain. What you have is some tricks to bound the memory usage. So what is going to happen is that if I try to prove all the blockchain transitioning one in one proof is never going to end. So we will have there are two optimizations possible. Standard supports only one. And the idea is that we are going to use a recursive proof. So we are going to write a verifier, in this case in Cairo, and we are going to prove that we have verified a proof, right? So you start making a tree. And that adds a lot of parallelizations to the proving, to the proof generation, because it's a tree of provers that each, for example, proves that it verifies two proofs, and the other one proves that it verifies the two proofs that have verified the other two proofs. That kind of structure, you can only do it efficiently with stars, and for me, it's one of the main advantages, because when you are working with elliptic curves, and you try to do that, if you remember the pairing function, we didn't talk about now. Okay, that is something that is key to proof of SNAR, that is a pairing function. And the thing is, it goes from one space to another space. And when you go to the other space, you are kind of screwed up when you try to write this kind of system when you verify, when you prove that you have verified something. But here in Starks, the good thing is we are always using the same field. We never go to another field. We never go to another curve or another subgroup. It's always the same. So your verifier in Cairo is going to be really efficient, and you can just keep adding provers as much as you need. Then there are two other optimizations that Starnet doesn't have, that Rich Zero and Maiden has. One is called continuations. And the idea of continuation is that you are going to... so, before going to continuations. Now, if I'm doing a recursive proof, the good thing is that the cost is always the same. Because it's always the cost of running a verifier in Cairo. So you can, no matter what you want to prove, if your proof is recursive, it's always use the same amount of resources. Okay. The other thing that you can do, leaving aside recursion, any question about recursion? Okay, is this idea of continuations? Since our program is basically a lot of steps of the VM, what we are going to do is to split the program. Just prove the VM up to some point, and then make another proof of the rest of the program. That's the core idea. So you start splitting the program and proving it in smaller chunks. And you can always even parallelize that, because you can start proving the chunks and then making like the thing you have to show him the proofs. That's it. That's another thing that is really useful about Starks in general. I have not seen that in other places, but it's really great.
Mauro, what makes a proof recursive?
The proof is recursive when you are proving that you have verified a proof. That's the recursion. And you can even swap systems. Is that clear, Marcos?
So sorry, you asked something?
Yeah. If that's clear. The recursion is I prove to you that I have verified the proof. Or maybe I prove to you that I have verified two proofs. And the recursion comes from this idea that I am proving that I'm verifying something, so it's kind of a recursive proof.
It's hard to imagine for me, right? Because for me, a proof is still it's a sequence of characters, right? So I imagine that recursive probably something that you can generate when you're going to verify or not.
No, you're proving an execution of a program, right? The program can be Fibonacci. The program can be a transference of funds. You can prove whatever you want. In particular, you can write the verifier in Cairo or in whatever and run the verifier as any program, because you can run any program. You can even run a verifier.
I see now. I understand. Yeah. Recursive in that sense. Yeah. Okay. Yes.
So yes. So since you can write any program, you can write a verifier and you prove to me that you have verified two proofs. And in one way, you are like parallelizing the proof generation, and that's something really powerful and kind of zipping it, because I make a proof that I have verified many proofs, so you only have to verify one now, not all of them.
Dude, that I don't know. That's more of a theoretical question. That seems to bring problems. I don't know how to pose this question, because that's the problem in the Turing completeness, right? If you want to prove that the halting problem, right? You invoke a program as a parameter of itself, right? So that's what basically you're doing here also.
Yes, in the case of
any problem. Well,
yes, in the case of StarNet, it's used for this parallelization. When you keep making a bigger tree and running more provers in parallel, and you are only adding like this delay, but you can add as many computation as you need.
But you need the input to shrink every time you call. You make a recursive call like that, right?
Yes, most leaving aside some data maybe of which hashes were used or something like that, leaving aside public data, yes, the proof is constant size.
I understand. Yeah. No. Yeah. I can imagine.
And it can be used in two manners. For example, in StarNet or in L2 that care about scalability, is used for parallelization. You add more provers and you get more throughput. It's incredible. Other proving systems like Mina, they don't have many parallels, but they have one that moves forward with the blockchain. And so the recursion is just it's not many provers in parallel, but one that goes to the infinite. And so they keep constant the size of the blockchain, more or less. That is a caveat there, but that's the idea. And that's if you go to Mina, more of the ads are like constant size blockchain. Okay. So that's recursion. And recursion gets even better and more funny, because I told you that you can write the same verifier in Cairo, but you could write another verifier. You can prove with stars that you have verified a snark proof. You can prove to me with a snark that you have verified a start proof. You can mix the systems. You can change the hashes. Maybe it's always stars, but the first layers we do it with hashes that are very good for the computer, and the other layers we do it with hashes that are really good for CK. For example, that's one trick to improve the speed of the recursion for scalability. The other trick is, okay, maybe we like this property of the stars where we parallelize the proving. But maybe we also like the property of some snark that lets you have a very concise or small proof that can be verified very fast in the blockchain because the pairing is part of the EVM, so it's cheaper. So in that case, you can go with stars all along, and at the final step, you make a star proof that you have verified the snark and convert it into a snark, and now it is a snark, and you send the snark to the blockchain. That's another trick some blockchains are doing. Okay, that was a small detour. Going back to the previous session, so continuations allow you to split the program and running in parallel, which is really useful. I think there was another optimization they had in Maiden, race 0, let me check. I know they were like two really good optimizations, but if not, I will continue with another thing that is really important. Okay, no. Then you might have read about something called built-ins. I'm not sure, in Cairo, maybe built-ins in Cairo, maybe chiplets in Maiden, or things like that. So what happens? Sorry, I need to get some more water because my throat isn't really good. Okay. So the idea is, what if we will have like another machine? Let's say we want to compute SHA, and we know that SHA takes a lot of steps. Yes, maybe we can make a small 5-minute break. And I drink the water. Okay. Yeah, if it's just 5 minutes, we can wait for Marcos, no problem. I need a break, so. Okay. I will repeat it if whenever Marcos comes, no problem. So we don't just stay here quiet. Any questions?
I have one. You were talking about the other trick that they will prove the Stark into the chain. May you repeat that again, please? I didn't catch it.
Can you repeat? Sorry, give me a second because there are some cars passing. Can you repeat the question?
You were talking about new tricks that Change are doing for Starks. So may you repeat that? It was the last sentence you said before Marcos was on.
About the trees, about proving a star with a snark. The thing about proving a star with a snark.
Yeah, that one.
Oh, the other way around. Okay. So I started saying that with stars you can make this recursive tree, where you're going to prove to me that you have verified a proof, right? And you can change the proving system. You can make, I don't know, a plum proof that you have verified a Stark, because you write the Stark verifier in something that it is used by Plonk, and so you can convert from one system to the other one. You can make a big tree of Starks, and in the final step, use maybe Plonk or something to prove the final verification, to say, I prove to you that I verified the Stark proof. And usually those proofs are more efficient in Ethereum. So that might be useful. And you use the scalability of the stars and the succinctness in Ethereum of a star.
Oh, got it. Okay, thanks.
Okay. So now let's keep optimizing this. So we have this idea that maybe we want to apply to use SHA, and SHA is really expensive. Or maybe you want to do bit operations, and bit operations are expensive. Just the bit operations are already expensive enough. What we would like to do is to have like another machine that is not the Cairo-vm, or it's not the Maiden-vm, or whatever VM we have, that is really good at solving that problem. That machine, in practical terms, it might be just the machine you're using. But the thing is that that we are going to want this a specific provable machine really good, for example, for SHA. In the case of Cairo, we are going to call that machine a built-in. In the case of Maiden, we are going to call a chiplet, and they are going to work a bit different, but let's go with a built-in. Maybe before the built-in, yes, okay, I have to explain something so you understand the built-in. Remember that Diego shows you this transitions, and you say, okay, we have this row, and it transition to this row, and it's transition to this row. And it was quite straightforward. Well, that in the case of Cairo is a simplification, because what you can have bigger cycles. You can take a cycle, for example, of 4 rows, and your transition is 4 rows long, or it can be 8 rows long. That doesn't add any problems. And for example, you can have all your flags that I show you as one column, you can have them all in one column. You can always do that. And if you watch our documentation in virtual columns, in the Lambda Wars repo, let me look at it. You can have any of these structures, and they are equivalent. You can have for each flag a column, or you can place them all in one column. This idea of one column, you will see it as a virtual column, because the cycle of the VM is going to be longer, because the transition is going to be between all of these, but the transition constraint, they are not going to be identical. For example, B0 transitions kind to B1, but not to A1. This is the idea of virtual columns or interleaving. We are going to use that for built-ins. So the built-in is going to have its own specific set of constraints that they are only useful, for example, to solve SHA. They can't do anything else. We are going to interleave our Cairo-vm trace with the values associated to the built-in, which is own set of constraints. And of course, if I have two machines, there should be a communication between them, because if I prove to you in somewhere that I use SHA and I have the VM that is doing its normal operation, I have to connect them. In the case of the Cairo-vm, this is done through the memory. There are some positions of the memory that are assigned to the built-in, and whenever there is a value that is on this memory position, they are affected by these additional constraints of the built-in. That's it. It's really straightforward. But this structure has a problem that makes it a bit inefficient, because let's say I have 3 rows for the VM and 1 for I don't know, the SHA built-in or whatever built-in. And I have a program that has 1 million steps, and I only use SHA once. So what's going to happen is that I will have a lot of rows assigned to the built-in that are not going to be used, but I will still have to prove them. So that's an additional overhead of the built-ins. If I know the program I'm using beforehand, they are really useful because you can optimize them. But if the program is too generic, maybe it's not going to be extremely efficient. An alternative is what Myriam does, that is called chiplets. And the idea of chiplets is that they are going to be communicating the VM and these other machines through a bus. Instead of sharing memory positions, all the communications with the building is going to be through buses. This is just computer engineering all over again. In one case, it's like the input devices of your machine where you share memory positions, and in the other case, it was like the CPU or whatever where you use a bus to communicate. The only problem of the bus is, of course, you have to prove the bus. And that can be quite tricky. I will not go there for today, but you can check it out. I just want you to have the idea of these chiplets and the built-ins. I think that covers everything you might need to know about how the VMs are proven. I'm not sure if I'm missing any useful trick that we use, Mariano, or that other virtual machine uses. Yeah, I think that pretty much covers everything. Do you have any questions? Okay, if some question arises and you want to ask later, you can do it in another talk or whatever.
Mauro, just to close, it's not actually about what you just it's what you just said. It's about the baby bear feel again. So, so you're going to take care of that part, or do I have to do something else on my side
About what?
about the PR?
Yes, your PR. I will try to take a look. So if you're having troubles and you already tried to solve it, I will.
Yeah, because I put the instruction any different places. It's not passing the check, right?
Yeah. Yes, I will take a look at it. Don't worry.
Okay.
We will try to solve it on our side. It shouldn't be that complicated. Marco is asking me about the PR he submitted as an issue.
Yeah.
So now that you know a bit how the VM works, you are free to implement things on it. Um, Marcos, I don't know if you want to try to change the sorting algorithm. You can.
Actually, that was another thing I was going to tell you. I want to do that this weekend, right? I already started writing it, and I want to do some benchmarks, right? Compare against the sort by procedure, and see if it is better or not using the start field, right? And that's it basically. If it is better, then I'll try to make a PR out of it, right?
That would be great.
Yeah.
Yes, maybe one last difference between VMs is what field they are using. The server is using a really big field. Mine is using Goldilocks, the small one. And ReZero is using Baby Bell. So that shows me that the VM is running with less speeds. But it's more a problem for the stars than the VM because a star might not be secure if the field is small. Maybe Diego will talk more about that in another day.
I actually asked this question to Diego this morning about Poseidon, and I think you know more, right? And you shared a small graphic where there is a hammer, a cross, and check marks and things like
Yeah.
that, right? What is missing in Poseidon?
Poseidon for me is missing. We have the Poseidon like how Starnet uses, but it's not general. Like maybe you want to change the MDS matrix, and I'm not sure you can do that really easily. And I think the sponge function might not be fully implemented. So yeah, there might be some issues when you change the field. We need to review that. I don't remember exactly. I have this in my mind. Maybe it's nothing big. I have to double check. We kinda just implemented it to work the same as Starnet and leave it there. There's also a fact that we should do because there are ifs inside the code, and there is no need for Poseidon to have branches inside. In particular, in Rust, maybe it doesn't matter a lot, but if you're doing that in a circuit, it's troublesome. Branches in the VMs are efficient, but in usual in your typical scenario is not efficient.
So I actually I would like to finish Baby Bear entirely, right? All the extension field. Also try to do this change the sorting algorithm. And actually I understand Poseidon pretty well. So if you have something there, I can try
Okay,
to make it also.
I will double check what we are missing and make an issue. At some point, we probably need a trait for the hashes. We were discussing that now. But we will probably do that change after someone submits Peterson rescue. So if someone wants to pick that to do it, it will be great. Perfect. Any other questions, maybe related to numbers or whatever? Okay. Another thing that may be useful if someone wants to do it on the start front, I think parallelization can be improved and some optimizations can be made in the Fourier transform. So if someone sees something that can be optimized, it's always good to be faster. Maybe we should make a small class about flame graph and optimization in general, so you don't start because maybe you're optimizing something that takes 1% of the time. So even if you make it 100 times faster, it doesn't matter. So you need to find the bottlenecks. but we can make another class for that. Maybe another lecture, or maybe someone can take that. Um, any other question? Well, if then we can finish for today. Let's see you all on Monday.
Okay, bye bye.
Take care. Bye.